So we'll start with a quick recap of the last part of session 6, where we were discussing about the basics of three-dimensional vectors. So we saw vector representation in three-dimensional coordinate system, or what we call three-dimensional component algebra. So this was what we were looking at last time, and we saw that any vector represented in three-dimensional component form is given by this kind of an equation, where the magnitude of the vector becomes square root of ex square plus ey square plus ez square. And the best way to visualize this vector is that you can imagine the vector E as the body diagonal of a cuboid with edges ex, ey, and ez. So let us understand this a little bit more detail. Yeah, I give you a chance to go up and go through this whole thing. So for students who have just about joined in, we have just started, not really missed anything yet. This is what we're looking at. Okay, so I see 3 or 4 people have just joined in. So we've just started discussing about reviewing what we did in the last lecture towards the end, which was representation of vectors in three-dimensional component form. So let's understand geometrically again what this all means. So imagine a cuboid like this. Where we have now, suppose, defined this corner as our origin, and gone on to define this as our x-axis, this as our y-axis, and this as our z-axis. So as you can see, this is like the floor of the cuboid. So this whole floor, the plane of this floor now represents the xz plane. Similarly, this surface is the yz plane. This whole surface now, this whole plane is the yz plane. So it's like one of the walls in your room, and the surface in front, let's say this one, represents another perpendicular surface, which is the xy plane. So these are three mutually perpendicular planes like this. So this is how we visualize the three-dimensional system. Now in this, if you visualize this vector or this edge of length Ex, then you can just think of this vector as the vector Ex I cap. Okay. Similarly, if you visualize this edge of the cube as of length Ay, like the height of the cube, that kind of thing. So this vector now represents Ey cap. And similarly, if you visualize this particular side as Ez, so this represents Ez k cap. So that's how you can first of all individually understand the three components: Ax along the x-axis, Ay along the y-axis, and Az along the z-axis. Okay. Now from this we'll understand what the vector A itself is, because next we have to construct the vector A, where the vector A is becoming the sum of Ax I cap plus Ay j cap plus Az k cap. So how come that vector is going to become the body diagonal? Let's understand that thing next. We'll come to that. Okay. So first make sure you are clear about this particular diagram. Okay. So here we've just drawn a cuboid and we said that okay, the three edges of the cuboid, the mutually perpendicular edges of the cuboid are of length Ax, Ay and Az. Okay. So that's why this particular edge from the origin, you can treat it like a displacement vector, which is Ax I cap. This particular edge from the origin to this corner, we can treat it like Ay j cap as a vector. And similarly, this vector becomes Az k cap. Okay. So now let's see how the summation of these three is going to work out. So let's redraw this diagram and understand. So let's again take this point as our origin, treat this as our x-axis, treat this as our y-axis, and treat this as our z-axis. The same diagram as the earlier one. So this one is our z-axis. Now we want to draw this vector, which is Ax I cap plus Ay j cap plus Ez k cap. Where in the earlier diagram we understood what was Ax I cap, Ay j cap, and Ez k cap. Those were these three. Okay. So let's understand that what happens when we sum them up. So let's use a similar type of logic that we've done for summation of vectors earlier. Okay. Just treating them like displacements. Okay. So starting from the origin is my initial point. I'm first making a displacement of Ex I cap. So that will look something like this. Then from there I'm making a displacement of Ay j cap. So now that one will look like what? I will have to draw Ay j cap from this point. So that will bring me to this corner. Bring me to this corner point. And then I'm completing my third displacement, which was Az k cap. So that will bring me from that point to this corner. So this is how the summation of Ax, Ay, and Ez is looking back to back. See, they are the same vectors, but they are now not, all three of them are not drawn from the origin. Instead, they are drawn as Ax. Then from the head of Ax, I have drawn Ay. Then from the head of Ay, I have drawn Az. So they are drawn back to back because we are doing this operation: Ex I cap plus Ay j cap plus Az k cap. So this is now the operation which is I have completed from the origin the displacement Ex I cap. Okay. Then after that, I have next completed the displacement Ay j cap, which is this vertical line like this, and then I have completed the third displacement, which was Az k cap, like this. So I have reached where I have reached this corner. Okay. So now my net vector, the net displacement, which is the sum of these three, is which one? It is from the origin to this point. Okay. So my resultant is now becoming this particular vector. My resultant is becoming this vector. So that's how it becomes the body diagonal. This is my vector T, which is the sum of Ex I cap plus Ay j cap. Okay, so this is how we understand that this vector now E represents the body diagonal. Let's say this corner point is called P. Okay. So body diagonal OP of the cuboid with edges Ex, Ey, Az. Okay. So just make a note of this if you want. Okay. Yeah, I can. In case you want to note down the above part first, you can just do this. So minimizing further will just make the print too small for everybody. So you can take your time, first understand this, then the part below. Okay, so if you're done with this, yeah, we'll do lots of examples, but first we want to understand the visualization of the vector. Example is just take Ax, Ay and Az as some numbers. So those numbers are just the edge lengths. So suppose it is 2 I cap plus 3 j cap plus 2 k cap. So those edge lengths are just 2, 3 and 2 again. Okay, Hari, I'll take the page up again. But this is all information that you have in last lecture's notes only. This is the recap part. Right, so this is all information from the last lecture. You have all this. We have discussed. Now we are looking at the interpretation of this, how to draw this as the body diagonal. vector is from this beginning of yeah, students, sorry, I just had a internet break. So yeah, so hope this diagram is now clear. So now let us also look at the next thing, which is that magnitude of E is given by root of ax square plus ay square plus az square. So let's understand the proof of how that works. So mod of vector E should be equal to square root of ax square plus ay square plus az square. So let's understand how this works out. Once again, if you imagine the cuboid, which has the given side lengths, right? So again, in this cuboid, let's say this point is A, and this point was our E, and this was our vector E finally. But before that, let's say this point is R, and this point is Q. Okay. So first, let us look at these two vectors that we had constructed: Ax I cap, which was this, and Ay j cap, which was this. So this was of length Ay, and this was of length Ax. And now let us imagine that we are looking at this triangle OQR, which is in fact lying, you can see in the XY plane. Just imagine this properly in 3D. So forget about the point P for the moment. Okay, just concentrate on this triangle that I've drawn over here. Triangle ORQ. Okay. In triangle ORQ, it lies, you can see, in the XY plane. Okay. You can see that angle ORQ is 90 degrees. Okay. And OR is of length AX, and RQ is of length AY. So by Pythagoras theorem, what will be the length OQ? It will be square root of AX square plus AY square. So let us say this is our equation 1. Okay. So just understand this and make a note of this first. Okay. So what we are trying to do next is we are trying to look at the proof of this. Okay, this equation, how we get. So So for that we have to show that the length OP, okay, so in this case we have to show that the length OP should be equal to root of ax square plus ay square plus az square. Where we also know that now the length OR is ax, the length RQ is ay. And next step we'll see that the length QP will be az. So making use of these geometrical facts, how we can arrive at this conclusion that the body diagonal's length is equal to root of ax square plus ay square plus az square. So to understand that, the first part is geometrical interpretation of this triangle ORQ. So just note down this fact first. Okay, so hope this is clear to all of you. Okay. Now, next thing in the same diagram, we will add our az k cap vector. So that is this vector going from Q to P. Okay. So this is az k cap vector. Okay, and that justifies why this QP should be equal to az. Okay, and now finally the vector OP is going to represent the vector E, which is the sum of bonus. So this is the vector E, where E is, we've seen earlier, Ex I cap plus Ey j cap plus Az k cap. So next step what we are going to do is, in the same diagram now, we are going to look at this other triangle. We are going to look at triangle OPQ, this triangle. Okay, so that is this particular triangle, and we are going to look at it from this side. So you'll see that when we look at it from that side, it looks like this. This is your side OQ, and this is your side QP, where this is AZ in length, and this is the side OP, which is basically the vector E. So its magnitude is E, and this corner point is. Now the important thing is, in this triangle, this angle will be 90. So in this triangle, angle OQP is equal to 90 degrees, because OQ is the face diagonal on the XY plane, okay, and QP is basically the edge along the Z axis. It's parallel to the Z axis. So this is a diagonal line in the XY plane, and this is a line lying parallel to the Z axis. So therefore they are perpendicular. Therefore OQ is perpendicular to. So just make sure you understand this interpretation properly. Just imagine you are looking at this shaded triangle OQP. P was this point over here. Looking at this from that side. From this side you're looking at it. So this angle will appear. That angle will be 90 degrees because of this reason. Yes, just imagine the cuboid as the room in which you are sitting. Okay. So, Shikhar, just imagine the cuboid as the rectangular room in which you are sitting. The wall that you are seeing in front of you, that is, let us say, the XY plane. Okay. So that is where that triangle ORQ lies. The wall that is right in front of where you're sitting, in front of your eyes, that one is the wall in which that triangle ORQ lies. Okay. So the bottom edge of that wall on the floor, that edge is OR, so that is AX, and the vertical height of that wall, that is AY. So what is OQ over there? OQ is the line which is the diagonal of that wall in front of you. Okay, so you see that right angle triangle ORQ. Now the wall which is to your right side, okay, that wall's top edge, that one is QP. Okay, so the edge made by the ceiling and the wall which is to your right hand side, that is your QP. Okay, and that is of EZ. Okay, so Q and P are joining the two corners of the wall which is to your right with the ceiling. So that is your QP. So now imagine you join the origin which is to your bottom left with those 2 points Q and P, which are the corner points of your right side wall on the top. So that is the triangle OQP that you are seeing, and that is why OP is perpendicular to QP. Okay. So now let us apply Pythagoras theorem in this triangle. So further in this triangle, we can see that OQ was equal to root of AX square plus AY square. This is from equation 1 above. Okay. And QP is equal to AZ. Okay. And the third one, OP is what we are trying to calculate, but OP's magnitude is the okay. So OP square should be equal to OQ square plus EP square. So this should happen. So E square should be equal to AX square plus EY square plus EZ square. So therefore you have your final relation. That magnitude of the vector E, which is capital E over here, root of Hitansh, I think if you keep a pen and paper in front of you, you're probably not noting down, which is why you're having trouble with understanding everything and asking me to keep going up and down. Keep writing down things in front of you. Make your lecture notes. Don't just listen to the lecture. If you don't write down, you will not understand these things. Okay. Then make properly, no? Okay, is it clear now, Itansh? Is there any other part which is not clear? Okay, so as you can see, this is a geometrical way of proving not only that the magnitude of a vector like this is root of ax square plus ay square plus az square, but this is actually a general proof of geometry that the body diagonal of a cube is such that it's square root of the length square plus the width square plus the height square. That is the magnitude of the body diagonal. Any cuboid which has dimensions like this, length, width and height, then the body diagonal of such a cuboid will have this kind of length. This is a way of proving it. Coordinates with three planes, any points, coordinates are written as x, y, z. Ananya. To answer your question, when you do three-dimensional coordinate geometry in maths, you will see that just like in 2D, we write the coordinates of a point as x, y. In 3 dimensions, we write the coordinates as x, y, z. And if a point is given by the coordinates x, y, z, then the distance of the point from the origin just becomes root of x square plus y square plus z square. Similarly, if you have 2 points A and B, which are x1, y1, z1, and another point B, which is x2, y2, z2, then the distance between the 2 points AB becomes root of x1 minus x2 whole square plus y1 minus y2 whole square plus z1 minus z2 whole square. But this is now coordinate geometry. Okay, this is not of concern to us right now. This is coordinate geometry. We are not really concerned with all this. We are concerned with this, which is component algebra of vectors. So we are more concerned with this thing, which is the component algebra of vectors. All right. So let's just do a couple of examples to understand this. So a particle makes a displacement of S1, which is, let's say, 10 kilometers towards east. Okay. Then S2, which is, let's say, 50 kilometers at 37 degrees north of west. Okay. And let's change this to meters instead of kilometers. And finally, S3, which is, let us say, 20 meters vertically upwards. Okay. So use a three-dimensional coordinate frame with x-axis towards east, y-axis towards north, and z-axis vertical. Okay. And represent S1, S2 and S3 in component form. And second, find the net displacement which is the sum of these three, okay, and its magnitude. So let's understand this question as an application of the three-dimensional component system that we just talked about. Just try this out, people. Yeah, Ritika, we just understood the derivation of the formula that magnitude of a three-dimensional vector system is root of ax square plus ey square plus ez square. So don't worry if you got disconnected, that formula will be there in your notes from last time also, and plus it will be there in the video recording, so you can pick it up after the lecture from the recording. Just try this question out, people. Okay, so I've got a lot of people giving me the answers so far, and it seems correct. Okay. So first of all, let us try to understand our coordinate frame properly. Okay. So basically, if I draw a two-dimensional horizontal plane, suppose this is your horizontal plane. This is a horizontal plane, like the floor on which you are sitting right now. So in this plane, your x and y axis will point like this. So this is, let's say, your x axis, this is your y axis. So this direction is towards north, and this direction is towards east. So that is towards west, this is towards south. And in this now, your z axis will be pointing like this, perpendicular to the plane. This will be vertical, opposite gravity. So for example, gravity will point like this over here. So if you drop an object, it will fall along the negative z axis with acceleration due to gravity towards the floor. So this is what we mean by our this thing. Okay. This is what we mean by, yeah. If you got disconnected in between, just carry on from this point onwards. Okay, and later you can go through the recording of the earlier part which you missed. I will send the link of the recording in a couple of hours after the lecture, so you can just catch up that point. Okay. So given this, now let us understand how we will represent these individual displacements S1, S2 and S3. Okay. So S1 and S2, you can see, are both displacements in the horizontal plane. They are both horizontal displacements. Whereas S3, because it is vertically upward, it is a vertical displacement. So to understand S1 and S2, we don't have to worry about the vertical at all. We have to just look at the horizontal plane. Okay? So let us understand S1 and S2 separately now. So suppose we are looking straight into our XY plane. So we are straight looking at our XY plane, which is a horizontal plane. So in this, we can see that S1 is the displacement towards the east and of 10 meters. So S1 is a displacement like this. So in component form, S1 will just be written as 10 I cap in meters. Alright, that is as per the information given. S1 S out, 10 meters towards the east. Okay. Now what about S2? It is 50 meters at 37 degrees north of west. So S2 kaisa hoga? S2 will be a displacement which is like this. It is 37 degrees north of west. So it will be like this. S2 on its own is a displacement which is at 37 degrees north of west. And its own magnitude is how much? Its own magnitude is 50 meters. Just like this. Okay. So this is the information. North of west. Okay. So now how we'll write S2 as a vector in component form. S2 which will have an x component of which is negative of how much? Minus 40. And a y component which is positive of plus 30. Because for the vector S2, the magnitude is 50, okay, and the angle with the x-axis is 153 degrees. Okay. So cos theta is minus 4 by 5, and sin theta is plus 3 by 5. So use these for the components, and you'll get minus 40 and plus 30 in meters. So that is your S2. Okay. And S3 is in this diagram coming out of this straight towards you. So you cannot draw the vector in this diagram at all. The S3, you can understand, is a vector in this diagram, which is like this. It's going vertically upwards. So in the diagram below, where you're looking into that horizontal plane, it's coming straight towards you. So in this diagram now, we cannot directly draw S3, but we can say that S3 is 20 k cap, because it is vertically upwards. So it's straight coming out of the plane, so it's along the z-axis. So this becomes my first part's answer. The individual displacements S1, S2 and S3 in component form are like this. Okay, so hope this is clear first of all, people. Now, next part, what you have to do, you have to find the net displacement, which is the sum of these. So, if you understood this now, you can work that out. Just work out the sum of these. Yes, that's correct, Kushant. Yes, that's correct. So now work out its magnitude. So S net will become, the sum of the x components is 10 minus 40 plus 0. So that is minus 30. Okay. Y component is plus 30 and Z component is plus 20. So square root of 2200. Yes, that's the correct answer. Okay. So this is our net displacement. Yes, Prajnesh is correct, your answer. Yes, Durgesh, tell me what is your doubt? How to express? So see, when Prajnesh, Itanj, you still not understood S2. Okay. Yeah, Durgesh, to answer your question, see, z-axis is pointing vertically upwards. So negative z-axis will be pointing downwards. Okay, negative x-axis will be pointing downwards. Okay. And Itanj, to understand the displacement S2, look at this diagram where I made S2's displacement. S2 is like this. This angle is 37. So the angle with the positive x-axis in the xy plane is 153 degrees. Okay, and its magnitude is 50. So its x component is 50 cos of 153 degrees. So that is 50 into minus cos 37 degrees. So that is 50 into minus 4 by 5. So that's why it's minus 4. Similarly, its y component is 50 sine 153 degrees. Now, second quadrant formula, sine 153 is positive of sine 37. So 50 into 3 by 5. So that's why it's plus 30. How we calculated the component form, Ritika, of S3? See, S3 is the vector which is lying along the z-axis. S3 is given to us. It's given to us in the question that the vector S3 is vertically upwards and it's of 20 meters. It is given to us that it's vertically upwards and it's of 20 meters. Okay. So come back to this diagram, you will understand where is S3 lying. It's lying along the z-axis. It does not have any horizontal component, so it does not have any xy component. Understood, Ritika? The vector S3 is straight vertically upwards, whereas the xy plane is which plane? It's the horizontal plane. So that is why the vector S3 does not have any component in the horizontal plane. So it does not have any xy component. It's straight upwards. Had it been straight into the earth through a tunnel, then it would have had a negative z component. If it has an xy component, it's a different matter. But here it does not. Right? It's a vertical vector. Okay? So that's why our net is becoming like this. Okay? And now the magnitude of the net displacement is square root of x square plus y square plus, yeah, Hari, just hang on. I'll discuss your point later. Okay? We're talking about this question first. Just stick to one question at a time. Okay? So let's see, it is 9 plus 9 plus 4 into 100. So this becomes the magnitude of the net displacement. So in this, very important, what we have to understand is that the vectors S1 and S2 are in the xy plane or the horizontal plane. Okay. So therefore, they do not have any z component. Okay. Whereas the vector S3, it is vertical. Okay. So therefore, it does not have any horizontal component. Okay. That is no x or y component. Okay. It is purely along z-axis. But when you sum up all of them, that is the whole point, no? That S net, which is the sum of S1, S2 and S3, this now has both vertical and horizontal components. So it has an X component of 30, it has a Y component of 30, and it has a Z component of 20. So that's how you're understanding the composition of a three-dimensional vector, no? How it's becoming. Practically speaking, this is how you're understanding the composition of the three-dimensional vector. Okay. So just take a minute to go through this once more and understand it completely. I'll scroll down also, just note down these points. Now, Hari, what you're asking about the angle of the resultant vector S net with respect to Z axis and all, we are coming to that. That is something called direction cosines. That's the next part we will learn. Okay, so 10 root 22, and now this is the additional points. Yeah, we can, Ritika, in principle, but then we have to know the angle between the vectors. Okay, so that becomes more complicated. Okay, so generally speaking, when we are adding three-dimensional vectors, we use, or generally speaking, when we are dealing with three-dimensional vectors, we use component algebra. We don't use geometry, because you know what happens. It's not possible to construct geometrical figures in 3D. In geometry, we are restricted to 2 dimensions because we are always constructing the figures on a 2 dimensional paper. Now, we are not making 3 dimensional models using sticks and all that. So that's why 3 dimensional vectors are only dealt with using component algebra and not using geometry. You have to remember that in our study of geometry, we are always limited to 2 dimensional geometry because we are constructing everything using a 2 dimensional diagram on a sheet of paper or on a screen. All right. Next thing we will understand about 3D vectors is the concept of direction cosines. Okay, Hitansh, I will give you a bit more time to write down. Just a moment, people. We will take some more time to understand these points and then. Purely along the z-axis. S3 is a vector which is purely along the z-axis. Okay, that is what we will do. Purely along the z-axis. Does not have any x or y component. Okay, good. So now let us move on to the next section. Next property of three-dimensional vectors, and we'll understand something called direction cosines. No problem with this. So now, if we are talking about a vector which has all three components x, y, and z, mutually perpendicular axis. Now let's think about a vector which is having all components x, y, and z. So for a vector given by the sum of three non-zero components ax, ay, and az. Okay. If the angle it makes with the x-axis directly is denoted by alpha, okay, the angle it makes with the y-axis, that is denoted by beta, and the angle it makes with the z-axis, that is denoted by gamma. Okay. Then the quantities cos alpha, cos beta, and cos gamma, they are collectively called direction cosines. Okay. So if you just drop an angle from the vector E with respect to each of these positive axes, x, y, and z axis, then those angles respectively are given by the symbols alpha, beta, and gamma. And the cosine of alpha, the cosine of beta, and cosine of gamma respectively are called the direction cosines. So this is just a definition. Just make a note of the definition of direction cosines first. So this will answer your question, Hari, that you were talking about. If we know the angles of a vector with respect to the x, y, z axis, how we can write the components. Next, we will understand that. Because it is more useful, right? Okay, when we write the formula of the direction cosine, we'll understand it's a more useful quantity. Okay, so next let's understand the formula. Cos alpha is given by the quantity Ex upon magnitude of the vector. Cos beta is given by Ey upon mod A, and cos gamma is given by Ez upon E, where E is of course the magnitude of the vector, which is root of Ex square plus Ey square plus Ez square. So for us right now, this is the important thing. The formula to get the value of the direction cosines, provided we know the components of the vector. Okay, so let's write down an example problem. Find alpha, beta, and gamma for the given vectors. Okay, just try this out, people. Now use the formula above to find out the angles. Just send me the answers, people. Cos alpha is half beta. Cos alpha is half. So for the first one, you see cos alpha is ax upon mod a. Now mod a for the first one is square root of 2 plus 2 plus 4. That is 2 root 2. So this becomes root 2 upon 2 root 2 or half. So cos alpha equals half means alpha equals to how much? 60 degrees. Cos beta is equal to Ey upon E. That is again root 2 upon 2 root 2 or half. So beta also equals 60 degrees. And cos gamma is equal to Ez, correct, upon E. So 2 upon 2 root 2. That's 1 by root 2. So that means gamma equals 45 degrees. So this is the three quantities, alpha, beta, and gamma for the first one. Okay, now similarly calculate for the second and third also. See, Somadip, now the thing is quadrants are only in the two-dimensional plane, XY plane. When we are talking about three-dimensional, we don't talk about quadrants. Okay. We just talk about the angle with respect to the positive x-axis, with respect to the positive y-axis, and with respect to positive z-axis. The whole concept of four quadrants is relatable with two-dimensional plane. Yes, that is correct, Yojit. Correct answer for second part. So for second, you should be getting alpha as 53 degrees, beta as 37 degrees, and gamma as 90 degrees. Which totally makes sense actually. If you interpret this, you'll understand that the vector E lies in the xy plane. That means it is perpendicular to z axis. That's why its gamma is 90 degrees and alpha equal to 53 degrees. So beta will have to be 90 minus 53. If it's lying in the two-dimensional plane, then this relation will have to hold true. Because it's in the two-dimensional plane, so there is this special relationship between alpha and beta. But जहाँ पे वो 2D plane में नहीं है, वैसा कोई relation नहीं है. Here you can see that alpha plus beta is not 90 in the first case because it is not lying in the xy plane. But in the second case, it's lying in the xy plane. For which one? For the second one, Drumi, or for the third one? Yeah, I'll come to the third one. Second one is very easy. Second one you can see now. In second question, you can see what is magnitude of A. It is 5. And what is AX? It is 3. What is AY? It is 4. And what is AZ? It is 0. Okay. So cos alpha is 3 by 5. Cos beta is 4 by 5. And cos gamma is 0. So that's how we are getting 90, 37 and 53. Yeah, Prashant, I'm coming to the third one. Your answers are correct mostly. Correct. Okay, so hope the second one is clear to everybody now. Yeah, third one, beta, one of the angles will be an obtuse angle because cos beta is negative. That's the only thing you have to be careful about. So in the third one, we are dealing with this vector I cap minus j cap. Right. So magnitude of the vector is root 2. Ax is 1. Ay is minus 1. Ez is 0. So therefore, cos alpha is 1 by root 2. So alpha is 45. But cos beta is minus 1 by root 2. So beta becomes 135 degrees obtuse. And cos gamma is 0. So gamma becomes 90 degrees. So you can see that if the third one, draw the vector, is lying in the xy plane. So it will be like this. So alpha is 45 degrees, but beta is the angle made with the y-axis. So that will be this angle, the positive y-axis. It's 135 degrees. And gamma is 90 because in the xy plane. Correct, Lushant, Pradnesh. Yeah, Shikhar. The first question we have seen already. Okay. So now we can also have a reverse question like this. Okay. Magnitude of a vector E is, let us say, 25 units. Okay, and alpha is equal to 60 degrees. Beta is equal to, let's say, 135 degrees. And gamma is equal to, let us say, 120 degrees. So express vector E in component form. So here now we'll use the reverse of that. We have cos alpha is equal to Ex upon E. So in other words, Ex can be expressed as E cos alpha. So that is 25 cos 60 degrees. So that's 25 by 2. Similarly, cos beta is defined as Ay by A. So from that you find out how much this is, how much Ay is. And similarly you find Az, and then finally express the vectors Ax I cap plus Ay j cap plus Az j cap. Okay, so Ay कितना हो जाएगा? 25 cos, correct. Rushant, correct. Cos 135 will be minus 1 by root 2. So this will become minus 25 by root 2. And similarly, Ez will also be negative. So there are more ways you can write this also. You can write this as 12.5. You can write this as minus 12.5 root 2 also. Similarly, cos gamma will become minus 25 by 2 or minus 12.5. So the vector E you can express, the most simple way of expressing it is directly like this: 25 by 2 I cap minus 25 by root 2 j cap minus 25 by 2 k cap. Okay. Or you can take something common and write it like this also. or you can express it as take 25 by 2 common, so it will become I cap minus root 2 j cap, so minus j cap. So there are all these different ways in which we can express the vector. So all of them are correct as long as we have written the components numerically correct. There is no problem. This is okay. This is okay. Okay, now one final thing about direction cosines, then we move on to the next thing. One final important aspect of direction cosines. Because cos alpha is ax by e, cos beta is ey by e, and cos gamma is ez by e. Therefore, as a rule always, cos square alpha plus cos square beta plus cos square gamma will always be equal to unity. It's an identity. Just note this down. Now you can see it's self-evident why this is the case, because this is ax by e. Which is nothing but unity. So just like in trigonometry, you have sine square theta plus cos square theta is unity. In three-dimensional components, you have cos square alpha plus cos square beta plus cos square gamma is equal to unity. So this is an important property for direction cosines. Okay, so this is all about direction cosines and three-dimensional vectors. Okay. Now moving on to the next thing. So we are now done with addition, subtraction, and all that of vectors using components. Now we come to the products part. So the next section we'll be studying is a totally new vector operation for us, and that is called the dot product. Or another name for it is scalar product. So this is, yes, Rumi, I'll scroll the screen for a moment. Right? Is it okay, Dhumi? Okay. Good. So now coming back to this new operation. So this is a vector operation. Now the symbol used for this operation is a dot. So it is read like this. Okay. So this symbol stands for dot product of vector A and B, or we can say it is scalar product of A and B. Note that we don't call it multiplication because this is not the same thing as multiplication. Multiplication is an operation that applies to scalar quantities. Okay? Here we are talking about an operation that applies to vector quantities, okay? And it is the symbol for it is this dot symbol. Now, what is the definition for it? Let's understand next. So the definition of the dot product is that to carry out this operation, we multiply the magnitude of vector A with the magnitude of vector B with cos of the angle between them. Okay, so this is the definition of the operation. This is the formula which tells us how to calculate the dot product, where E is nothing but magnitude of vector A, B is nothing but magnitude of vector B, and theta is the angle between the two vectors. Okay, so in this case between E and B. So start by noting down this part, okay, the symbol and the definition of the new operation. Then we look at examples. So don't relate this with multiplication or anything like that that we've learned before. This is just something new for us. This is a new definition that, how do we calculate the dot product of two vectors? This is the formula. It is magnitude of vector A multiplied by magnitude of vector B multiplied by cos of the angle between them. So we need to know three things to be able to calculate dot product. We need to know the magnitudes of vectors A and B, and we need to know the angle between them. No, this is a definition. This is not a derivation. Right? This is not a derivation. This is a definition. I am telling you, it's not been derived. It's a definition. It's a basic definition. We'll do some examples and you'll understand. Okay? So if we put a dot between two vectors, it means that we are doing this operation. We are calculating the scalar product of the two vectors, and that is given by the formula EB cos theta. Okay, so let's understand an example. This is what dot means. This is what the dot product means. This is the definition of the dot product. Okay. This is what it means. It is magnitude of A multiplied by magnitude of B multiplied by cos theta. There's nothing difficult to understand in this. This is just a new definition. Suppose vectors A and B are like this. that this angle is, let us say, 60 degrees. And they have magnitudes of 10 units and 12 units respectively. And I ask you, what is A dot B? It's very simple. A dot B will become E into B into cos of theta between them. So here it will be 10 units multiplied by 12 units, whatever that unit is, multiplied by cos of 60 degrees. So it will be 10 into 12 into half square. It will become 60 square units. Now, before you note this down, let's take another example. Now suppose we are having an inclined plane like this, which is inclined at 37 degrees to the horizontal. Now there's a particle or something. Now on that particle, suppose we decide to apply a horizontal force like this. So F is a horizontal force of magnitude, let us say 20 newtons, okay, applied on the body P as shown. Okay. So this is our body. Now as a result of application of this force, let's say this body makes a displacement and reaches up here after some time. Okay, so it makes a displacement. Now P makes a displacement S of magnitude 10 meters as shown. Now calculate dot product of force with displacement. This is what I asked you. Okay. So now you'll see that dot product of force and displacement, I'll have to understand that the force is a vector which is in this sort of direction, and the displacement is a vector which is in this sort of direction, and the angle between these two vectors is this one. It's 37 degrees. Okay. In fact, we'll see that the displacement is a vector which has a magnitude of 10 meters, okay, and the force has a magnitude of 20 newtons. So now our dot product will simply come from the formula magnitude of force multiplied by magnitude of displacement multiplied by cosine of angle between them. So 20 newtons multiplied by 10 meters multiplied by cos of 37. So that will become 20 into 10 into cos 37 is 4 by 5 Newton meter, and Newton meter is the same thing as joule. So here you will see that this will become how much? 160 Newton meter, or you can say 160 joules. So this will be F dot S. So later we study in physics that this is defined as work done by the force. It's defined that way. So don't worry about the definition of work done just now. That will come in a chapter called work energy. This is another example of how we apply dot product. Start with this first example, then I'll take you to the one below. So anytime we are calculating the dot product of two vectors, we just apply this definition. It is magnitude of one vector into magnitude of the other vector multiplied by cosine of the angle between them. Okay, so hope this first example is clear. Now come to this one. So this is how we'll be using dot product in future in physics. When we study a chapter called work energy, for example, and we want to calculate work done by a force, we'll see the definition that work done by a force F through a displacement S is defined as this. So that will be one of the practical applications of dot product. But right now, our concern is not the application thing. The concern is how to actually do the dot product calculation. So this is how we use the formula of dot product. So in this case, as the body is moving like this along this, all the time we are continuously applying the force horizontally only. We're not changing the angle at which the force is acting. A force is continuously acting. Imagine you are continuously pressing it with that horizontal force against the inclined plane, but that's causing it to slide upwards. Okay, so this is the definition of dot product. So next I'll look at a few more things about dot product from the definition. So E dot B is equal to EB cos theta. So let's understand a few aspects about dot product from this. So the first thing is that E dot B is a scalar, okay, because it is EB cos theta. So this thing, it has only magnitude, in no direction. So again, remember, work is a scalar quantity, whereas force and displacement are vector quantities. So it's such an operation that when we apply it on two vectors, it gives us what kind of quantity? It gives us a scalar quantity. Okay? So dot product results in a scalar quantity. Now next thing you can see, very important. is if theta is equal to 90 degrees, E dot B becomes 0. Okay. So dot product of perpendicular vectors is 0. Okay, so in this, next thing you see that if theta is acute, that is theta is less than 90 degrees, cos theta is a positive quantity. So E dot B is positive. Whereas if theta is obtuse, that is theta is greater than 90, less than equal to 180 degrees, then cos theta is negative. So E dot B can become a negative quantity also. So this is another important property of dot product, that the dot product of two vectors can be 0 also, it can be negative also, it can be positive also. For example, if I have two vectors which are let's say like this, say at an angle of 120 degrees. So E dot B here will become minus 50 because cos 120 minus half. Okay. Next property of dot product we understand is dot product of a vector with itself is square of its magnitude, because E dot A is E into cos 0, and cos 0 is 1. This is a very obvious property. Okay. Next, A dot B is the same thing as B dot A. It's the same thing as AB cos theta. So whether you write this as B into A into cos theta or A into B into cos theta, it makes no difference. Okay. So this is called the commutative property. Like scalar multiplication or like addition for that matter, it is commutative. A plus B is equal to B plus A. Like that, A dot B is equal to B dot A. And along with this, we also have the distributive property. That is A dot of B plus C is equal to A dot B plus A dot C. For example, in scalar operations, both multiplication and division are distributive. So like that, here dot product is also distributive. Alright, so hope this is clear. Now similarly, next up, let us understand dot product in component form. So for that, first we'll understand these properties that I cap dot I cap will be 1 because it's a unit vector. Dot product with itself is magnitude square. So similarly, j cap dot j cap is j is magnitude square, so that is 1, and k cap dot k cap is 1. However, if you take I cap dot product with j cap, it will give you 0 because they are perpendicular vectors. J caps dot product with k cap will be 0. Again, they are perpendicular vectors. And similarly, k's dot product with I will be 0 because they are perpendicular. So as far as the base unit vectors or standard unit vectors are concerned, dot product with self gives you 1. Dot product with any other unit vector gives you 0. So just note down this first. Okay. Now, for example, if I want to do something like this, vector E is suppose 2 I cap and vector B is 3 I cap plus 4 j cap, and I ask you what is A dot B. So I have two options. One is I can do this geometrically. I can draw the vectors. So I can see that vector E is suppose like this. So magnitude 2 lying along the x-axis. So in comparison, how will vector B be looking? Just using the geometry, you can understand that will be such that from this you can see magnitude of B will be 5, okay, and the angle it makes will be tan inverse of y by x, so 53 degrees. Okay. So geometrically I can understand that, okay, this is 53 degrees. So E dot B, by that geometrical definition, EB cos theta is 2 into 5 into cos 53. So that becomes 8. Okay. So that's one method. But we have a much easier method now. Okay. I have a component algebra method where what I'll do is I'll directly substitute E as 2 I cap and B as 3 I cap plus 4 J cap. Then the first thing I'll use is commutative property. So E dot B plus C can become E dot B plus of this. Okay. So this is 6 I cap dot I cap, which we just seen from the property is unity, whereas this is 8 I cap dot J cap. Now we know that I cap dot J cap is 0. That's the property of dot product because they are perpendicular vectors. So this is 0 and this is 1. So our answer is how much? It is 6. So E dot B should be 6. And above also it should be 6. I made a mistake with the value of cos 53. The value of cos 53 is not, so this will also give us 6. Because this is 2 into 5 into 3 by 5. So, 6, okay. So just make a note of this, people. Okay, so let us look at the second method also, where you're opening this by using the distributive property. So this method is the more important one for us, and we will see that we can actually now generalize this. Okay. So next up, we'll see the general formula. When we are given in component form, we won't use the cos theta method. Okay. We'll use this method that if the two vectors A and B are known in component form, just expand this. So this is AX plus AY plus AZ. Okay. Dot product with BX plus BY plus BZ. Okay. Now, when opening this, keep in mind that what is happening. We know that I cap dot J cap is 0. We know that J cap dot K cap is 0, and K cap dot I cap is 0. Whereas we know that, on the other hand, we know that I cap dot I cap is 1, J cap dot J cap is 1, and K cap dot K cap is 1. So when you expand this algebraically, there will be 3 into 3, 9 terms. But in those 9 terms, which ones will survive? Let's see. Okay. So the first term here with the first term here is I cap dot I cap. So that remains. So that is AX into BX. But then AX I cap dot product with BY J cap, that becomes 0 because I dot J is 0. So that doesn't remain. Then similarly, I cap with K cap, it becomes 0. So that doesn't remain. Then the middle term, dot product. So J cap with I cap again becomes 0. But J cap with J cap becomes 1. So we have EY BY. And again, J dot K is 0. Then the last term, AZ K cap, is dot product with I cap and J cap is 0. So only the third term remains. So that is AZ BZ. So this now gives us a simple formula of how to calculate the dot product in component form. So if we know the vectors geometrically, then we use the definition AB cos theta. If we know the vectors in component form, we just use this. Okay. So now any vectors are given to us in component form, we can directly use this. Okay. So for example, if the vector A is, let us say, I cap plus 2J cap plus K cap, and the vector B is, let's say, I cap minus J cap plus 2K cap. Now A dot B will become how much? So by this formula, you will see that A dot B will become product of X components, so that is 1 into 1, plus product of Y components, so that's 2 into minus 1, plus product of Z components, so that's 1 into 2. So that will now become 1. So that dot product is in fact equal to 1 minus 2 plus 2, so that's 1. So dot product of A dot B is 1 in this case. So this, as you can see, is a very easy method for vectors given in component form. Okay, people. So we've learned two important things today. We've learned the concept of direction cosines for three-dimensional vectors or vectors in general, and then we've learned the whole new operation of dot product. Okay, we saw the definition of dot product, and we saw all these properties, including the final one, which is this shortcut formula of finding the dot product when the vectors are known in component form. Okay, so make sure you revise through this very carefully and discuss any doubts from the notes if you have with me directly, and of course I'll be sending you a worksheet number 5 for you, which will have application of dot product also and some questions from the revision of the last few lectures also. So we'll have a mixture of questions. So try that out and discuss with me over the week. Okay. So that's it for today's class, people. Wish you all the best and stay safe at home. And until next lecture, whatever doubts you have, you can keep sending me on WhatsApp, please. Okay. Also, when you go through your test paper questions which you gave last Sunday, and if you have any questions in that you haven't understood, you can send that to me also. You can send a screenshot of the question, and whatever working you've done, I'll help you out with it if required. Okay. That's it. Thank you.